Welcome to this lightning talk about programmable systems for probabilistic modeling and inference. My name is Feras Saad. I'm an assistant professor at the Computer Science Department at CMU. A central question that drives my research is how can we develop scalable programmable systems that enable flexible probabilistic modeling and sound probabilistic inference? To motivate this question, I'll show a few examples of application areas where we might use probabilistic models to make interesting inferences about complex real-world data. In epidemiology, for example, one of the major surprises during the coronavirus pandemic is that COVID is extremely deadly to certain groups of people, but much less harmful to other groups, often in very unpredictable ways. So we might like to build statistical algorithms that can automatically extract these different groups and stratify them according to their expected immune response to COVID. The second example is econometric modeling, where we have very complex data of economic variables, such as the labor force, and we'd like to discover interpretable patterns such as seasonal variation, linear trends, and change points that drive the data generating process. We'd like to use these patterns both to explain the data to policymakers and also generate forecasts about likely future values. A third example is better understanding human cognition. So here on the slide, I'm showing three different figures labeled 1, 2, 3, and a human can very quickly understand how the numbers are related to the images. We'd like to engineer intelligent systems that embody the same types of symbolic reasoning principles that enable humans to perform strong inductive reasoning capabilities. So now that I've introduced a few application areas where probabilistic models are used, I'll next explain how probabilistic programs let us express very flexible probabilistic models. And the way that I'll explain this idea is by way of an example. So here I have some images of objects on a table, and suppose our goal is to build a system that takes one of these images and infers how many objects are on the table and what are their types and locations. In practice, we might use a depth sensor, such as the Microsoft Kinect, to make this type of inference. The way we use probabilistic programs to attack this problem is by writing a computer program that specifies a prior probability distribution over the range of images we might encounter in the real world. So in this program, on line 2, we sample a random number of objects to put on the scene. Here's 4. And then on lines 3 through 10, for each of these objects, we sample its type from some known universe of types, and then their three-dimensional rotation and location coordinates, rendered here. On line 11, we pass the objects through an image renderer to produce an idealized image, and then on line 12, we add some camera noise to produce a more realistic depth image. If we run the program again, we would get a different realization of objects and images. And we can run the program many times to get a sense of the prior probability distribution over the objects and images. Now, probabilistic programming is interested in working in reverse, which is we have observed our noisy image coming from our depth sensor, and we'd like to infer likely values of all of the unobserved variables in lines 2 through 11. This is a process known as probabilistic inference, where we're conditioning our probability distribution on a given observation of the image. So one sensible inference in this setting might be these three particular objects on the slide. But it turns out we can use the same program to answer a range of other inference queries, such as being given a partial image and filling in the occluded parts, or using a large data set of real-world images to learn these different noise parameters that characterize our uncertainty about the objects. The second major component of probabilistic programming is probabilistic inference. And I won't talk too much about it, but there's a range of systems that offer fully automatic inference in more restricted languages to highly programmable inference in more expressive languages that are geared for machine learning engineers. In the last decade or so, probabilistic programming has really proliferated across many different research areas: statistics, artificial intelligence, machine learning, and also programming languages, theory and applications and systems, and other application areas such as bioinformatics and scientific simulation. And these are just some key references of papers that have either introduced probabilistic programming ideas or leveraged probabilistic programs for interesting applications. A central area that I'm interested in is how do we synthesize these probabilistic programs from data? This is a very challenging problem because it's not always obvious how to get the right probabilistic program for your application. So here's an example where we have some data that's streaming in, and we might be interested in automatically building a probabilistic program that captures the data generating process. Now, if we're eyeballing this data, we can pretty much get a sense of the periodic repetitions, and also the increase in the value of the variable over time. Probabilistic program synthesis is this idea of using the observed data on the left to synthesize a probabilistic program on the right that captures the essential features of the data, which can then be used to formulate predictions of future data, which are shown in green. So here we're automating the process of constructing these probabilistic programs, which we could then use to solve a range of downstream tasks. It turns out if we actually evaluate these quantitatively on real-world economic data, the forecasts are very competitive with solutions from machine learning, statistics, and other approaches to forecasting. A second application area that I work in is more on the programming languages and systems engineering side, which is building specialized systems that aim to reduce the implementation complexity of probabilistic programs, reduce their wall clock runtime, and reduce the programming errors that show up in these very complicated probabilistic modeling and inference pipelines. The third area that I work in is in the theoretical or quantitative characterization of these programs, trying to formalize their properties, how well they fit a given data set, or try and estimate bounds on their resource consumption. And this is a lot of where the interplay between programming languages and statistical and probabilistic modeling comes in. And a final area I'd like to point to is these different applications that I'm very excited about. I showed a little bit of economic forecasting, maybe spatiotemporal modeling, learning bounds on program execution, but also other applications in the life sciences, such as building motion models of how zebrafish hunt their prey. Thank you.